A tropical cyclone is a rapidly rotating storm system characterized by a low-pressure center, a closed low-level atmospheric circulation, strong winds, and a spiral arrangement of thunderstorms that produce heavy rain. Depending on its location and strength, a tropical cyclone is referred to by different names, including hurricane, typhoon, tropical storm, cyclonic storm, tropical depression, and simply cyclone. A hurricane is a tropical cyclone that occurs in the Atlantic Ocean and northeastern Pacific Ocean, a typhoon occurs in the northwestern Pacific Ocean, and a cyclone occurs in the South Pacific or Indian Ocean. Tropical cyclones typically form over large bodies of relatively warm water. They derive their energy through the evaporation of water from the ocean's surface, which ultimately recondenses into clouds and rain when moist air rises and cools to saturation. This energy source differs from that of mid-latitude cyclonic storms, such as nor'easters and European windstorms, which are fueled primarily by horizontal temperature contrasts. The strong rotating winds of a tropical cyclone are a result of the conservation of angular momentum imparted by the Earth's rotation as air flows inwards toward the axis of rotation. As a result, they rarely form within 5 degrees of the equator. Tropical cyclones are typically between 100 and 2,000 kilometers, 62 and 1,243 miles, in diameter. They are far less common south of the equator, mainly because the African easterly jet, warmer waters, and areas of atmospheric instability, which gives rise to cyclones in the Atlantic Ocean and Americas, occur in the northern hemisphere, and because vertical wind shear is much stronger south of the equator, which typically prevents tropical depressions and potential storms from developing into cyclones. Tropical refers to the geographical origin of these systems, which form almost exclusively over tropical seas. Cyclone refers to their winds moving in a circle, whirling round their central clear eye, with their winds blowing counterclockwise in the northern hemisphere and blowing clockwise in the southern hemisphere. The opposite direction of circulation is due to the Coriolis effect. Coastal regions are particularly vulnerable to the impact of a tropical cyclone, compared to inland regions. The primary energy source for these storms is warm ocean waters, therefore these forms are typically strongest when over or near water, and weaken quite rapidly over land. Coastal damage may be caused by strong winds and rain, high waves, due to winds, storm surges, due to severe pressure changes, and the potential of spawning tornadoes. Tropical cyclones also draw in air from a large area, which can be a vast area for the most severe cyclones, and concentrate the precipitation of the water content in that air, made up from atmospheric moisture and moisture evaporated from water, into a much smaller area. This continual replacement of moisture-bearing air by new moisture-bearing air after its moisture has fallen as rain, may cause extremely heavy rain and river flooding up to 40 kilometers, 25 miles, from the coastline, far beyond the amount of water that the local atmosphere holds at any one time. Though their effects on human populations are often devastating, tropical cyclones can relieve drought conditions. They also carry heat energy away from the tropics and transport it toward temperate latitudes, which may play an important role in modulating regional and global climate. Physical structure. Tropical cyclones are areas of relatively low pressure in the troposphere, with the largest pressure perturbations occurring at low altitudes near the surface. On Earth, the pressures recorded at the centers of tropical cyclones are among the lowest ever observed at sea level. The environment near the center of tropical cyclones is warmer than the surroundings at all altitudes, thus they are characterized as warm core systems. Wind field. The near-surface wind field of a tropical cyclone is characterized by air rotating rapidly around a center of circulation while also flowing radially inwards. At the outer edge of the storm, air may be nearly calm, however, due to the Earth's rotation, the air has non-zero absolute angular momentum. As air flows radially inward, it begins to rotate cyclonically, counterclockwise in the northern hemisphere, and clockwise in the southern hemisphere, in order to conserve angular momentum. At an inner radius, air begins to ascend to the top of the troposphere. This radius is typically coincident with the inner radius of the eye wall, and has the strongest near-surface winds of the storm. Consequently, it is known as the radius of maximum winds. Once aloft, air flows away from the storm's center, producing a shield of cirrus clouds. The previously mentioned processes result in a wind field that is nearly axisymmetric. Wind speeds are low at the center, increase rapidly moving outwards to the radius of maximum winds, and then decay more gradually with radius to large radii. However, the wind field often exhibits additional spatial and temporal variability due to the effects of localized processes, such as thunderstorm activity and horizontal flow instabilities. In the vertical direction, winds are strongest near the surface and decay with height within the troposphere. Eye and center. At the center of a mature tropical cyclone, air sinks rather than rises. For a sufficiently strong storm, air may sink over a layer deep enough to suppress cloud formation, thereby creating a clear eye. Weather in the eye is normally calm and free of clouds, although the sea may be extremely violent. The eye is normally circular in shape, and is typically 30 to 65 kilometers, 19 to 40 miles, in diameter, though eyes as small as 3 kilometers, 1.9 miles, and as large as 370 kilometers, 230 miles, have been observed. The cloudy outer edge of the eye is called the eye wall. The eye wall typically expands outward with height, resembling an arena football stadium. This phenomenon is sometimes referred to as the stadium effect. The eye wall is where the greatest wind speeds are found. Air rises most rapidly, clouds reach to their highest altitude, and precipitation is the heaviest. The heaviest wind damage occurs where a tropical cyclone's eye wall passes over land. In a weaker storm, the eye may be obscured by the central dense overcast, which is the upper-level cirrus shield that is associated with a concentrated area of strong thunderstorm activity near the center of a tropical cyclone. The eye wall may vary over time in the form of eye wall replacement cycles, particularly in intense tropical cyclones. Outer rain bands can organize into an outer ring of thunderstorms that slowly moves inward, which is believed to rob the primary eye wall of moisture and angular momentum. When the primary eye wall weakens, the tropical cyclone weakens temporarily. The outer eye wall eventually replaces the primary one at the end of the cycle, at which time the storm may return to its original intensity. Rapid deepening. On occasion, tropical cyclones may undergo a process known as rapid deepening, a period in which the minimum sea level pressure of a tropical cyclone decreases by 42 mb in a 24-hour period. In order for rapid deepening to occur, several conditions must be in place. Water temperatures must be extremely high, near or above 30 degrees Celsius, 86 degrees Fahrenheit, and water of this temperature must be sufficiently deep such that waves do not upwell cooler waters to the surface. Wind shear must be low. When wind shear is high, the convection and circulation in the cyclone will be disrupted. Usually, an anticyclone in the upper layers of the troposphere above the storm must be present as well. For extremely low surface pressures to develop, air must be rising very rapidly in the eye wall of the storm, and an upper-level anticyclone helps channel this air away from the cyclone efficiently. Size. There are a variety of metrics commonly used to measure storm size. The most common metrics include the radius of maximum wind, the radius of 34-knot wind, that is gale force, the radius of outermost closed isobar, ROCI, and the radius of vanishing wind. An additional metric is the radius at which the cyclone's relative vorticity field decreases to 1 times 10⁻⁵s-1. On Earth, tropical cyclones span a large range of sizes, from 100 to 2,000 kilometers, 62 to 1,243 miles, as measured by the radius of vanishing wind. They are largest on average in the Northwest Pacific Ocean Basin and smallest in the Northeastern Pacific Ocean Basin. If the radius of outermost closed isobar is less than 2 degrees of latitude, 222 kilometers, 138 miles, then the cyclone is very small or a midget. A radius of 3 to 6 latitude degrees, 333 to 670 kilometers, 207 to 416 miles, is considered average-sized. Very large tropical cyclones have a radius of greater than 8 degrees, 888 kilometers, 552 miles. Observations indicate that size is only weakly correlated to variables such as storm intensity, that is maximum wind speed, radius of maximum wind, latitude, and maximum potential intensity. Size plays an important role in modulating damage caused by a storm. All else equal, a larger storm will impact a larger area for a longer period of time. Additionally, a larger near-surface wind field can generate higher storm surge due to the combination of longer wind fetch, longer duration, and enhanced wave setup. The upper circulation of strong hurricanes extends into the tropopause of the atmosphere, which at low latitudes is 15,000 to 18,000 meters, 50,000 to 60,000 feet. Physics and energetics. The three-dimensional wind field in a tropical cyclone can be separated into two components, a primary circulation and a secondary circulation. The primary circulation is the rotational part of the flow, it is purely circular. The secondary circulation is the overturning, in up out down, part of the flow, it is in the radial and vertical directions. The primary circulation is larger in magnitude, dominating the surface wind field, and is responsible for the majority of the damage a storm causes, while the secondary circulation is slower but governs the energetics of the storm. Secondary circulation, a Carnot heat engine. A tropical cyclone's primary energy source is heat from the evaporation of water from the ocean's surface, which ultimately recondenses into clouds and rain when the warm moist air rises and cools to saturation. The energetics of the system may be idealized as an atmospheric Carnot heat engine. First, inflowing air near the surface acquires heat primarily via evaporation of water, that is latent heat, at the temperature of the warm ocean surface. During evaporation, the ocean cools and the air warms. Second, the warmed air rises and cools within the eye wall while conserving total heat content. Latent heat is simply converted to sensible heat during condensation. Third, air outflows and loses heat via infrared radiation to space at the temperature of the cold tropopause. Finally, air subsides and warms at the outer edge of the storm while conserving total heat content. The first and third legs are nearly isothermal, while the second and fourth legs are nearly isentropic. This in up out down overturning flow is known as the secondary circulation. The Carnot perspective provides an upper bound on the maximum wind speed that a storm can attain. Scientists estimate that a tropical cyclone releases heat energy at the rate of 50 to 200 exajoules, 1018 J, per day, equivalent to about 1 pW, 1015 watt. This rate of energy release is equivalent to 70 times the world energy consumption of humans and 200 times the worldwide electrical generating capacity, or to exploding a 10 megaton nuclear bomb every 20 minutes. Interaction with the upper ocean. The passage of a tropical cyclone over the ocean causes the upper layers of the ocean to cool substantially, which can influence subsequent cyclone development. This cooling is primarily caused by wind-driven mixing of cold water from deeper in the ocean with the warm surface waters. This effect results in a negative feedback process that can inhibit further development or lead to weakening. Additional cooling may come in the form of cold water from falling raindrops. This is because the atmosphere is cooler at higher altitudes. Cloud cover may also play a role in cooling the ocean, by shielding the ocean surface from direct sunlight before and slightly after the storm passage. All these effects can combine to produce a dramatic drop in sea surface temperature over a large area in just a few days. Major basins and related warning centers. There are 6 regional specialized meteorological centers, RSMCs, worldwide. These organizations are designated by the World Meteorological Organization and are responsible for tracking and issuing bulletins, warnings, and advisories about tropical cyclones in their designated areas of responsibility. In addition, there are 6 Tropical Cyclone Warning Centers, TCWCs, that provide information to smaller regions. The RSMCs and TCWCs are not the only organizations that provide information about tropical cyclones to the public. The Joint Typhoon Warning Center, JTWC, issues advisories in all basins except the northern Atlantic for the purposes of the United States government. The Philippine Atmospheric, Geophysical and Astronomical Services Administration, PAGASA, issues advisories and names for tropical cyclones that approach the Philippines in the northwestern Pacific to protect the life and property of its citizens. The Canadian Hurricane Centre, CHC, issues advisories on hurricanes and their remnants for Canadian citizens when they affect Canada. On March 26, 2004, Hurricane Katrina became the first recorded South Atlantic cyclone, striking southern Brazil with winds equivalent to Category 2 on the Saffir-Simpson hurricane scale. As the cyclone formed outside the authority of another warning center, Brazilian meteorologists initially treated the system as an extratropical cyclone, but later on classified it as tropical. Formation. Worldwide, tropical cyclone activity peaks in late summer, when the difference between temperatures aloft and sea surface temperatures is the greatest. However, each particular basin has its own seasonal patterns. On a worldwide scale, May is the least active month, while September is the most active month. November is the only month in which all the tropical cyclone basins are active. Times. In the northern Atlantic Ocean, a distinct cyclone season occurs from June 1 to November 30, sharply peaking from late August through September. The statistical peak of the Atlantic hurricane season is September 10. The Northeast Pacific Ocean has a broader period of activity, but in a similar time frame to the Atlantic. The Northwest Pacific sees tropical cyclones year-round, with a minimum in February and March and a peak in early September. In the North Indian Basin, storms are most common from April to December, with peaks in May and November. In the Southern Hemisphere, the tropical cyclone year begins on July 1 and runs all year round, encompassing the tropical cyclone seasons, which run from November 1 until the end of April, with peaks in mid-February to early March. Factors. The formation of tropical cyclones is the topic of extensive ongoing research and is still not fully understood. While 6 factors appear to be generally necessary, tropical cyclones may occasionally form without meeting all of the following conditions. In most situations, water temperatures of at least 26.5 degrees Celsius, 79.7 degrees Fahrenheit, are needed down to a depth of at least 50 meters, 160 feet. Waters of this temperature cause the overlying atmosphere to be unstable enough to sustain convection and thunderstorms. Another factor is rapid cooling with height, which allows the release of the heat of condensation that powers a tropical cyclone. High humidity is needed, especially in the lower to mid-troposphere, when there is a great deal of moisture in the atmosphere. Conditions are more favorable for disturbances to develop. Low amounts of wind shear are needed, as high shear is disruptive to the storm's circulation. Tropical cyclones generally need to form more than 555 kilometers, 345 miles, or 5 degrees of latitude away from the equator, allowing the Coriolis effect to deflect winds blowing towards the low-pressure center and creating a circulation. Lastly, a formative tropical cyclone needs a pre-existing system of disturbed weather. Tropical cyclones will not form spontaneously. Low-latitude and low-level westerly wind bursts associated with the Madden-Julian oscillation can create favorable conditions for tropical cyclogenesis by initiating tropical disturbances. Locations. Most tropical cyclones form in a worldwide band of thunderstorm activity near the equator, referred to as the Intertropical Front, ITF, the Intertropical Convergence Zone, ITCZ, or the monsoon trough. Another important source of atmospheric instability is found in tropical waves, which contribute to the development of about 85% of intense tropical cyclones in the Atlantic Ocean and become most of the tropical cyclones in the eastern Pacific. The majority forms between 10 and 30 degrees of latitude away of the equator, and 87% forms no farther away than 20 degrees north or south. Because the Coriolis effect initiates and maintains their rotation, tropical cyclones rarely form or move within 5 degrees of the equator, where the effect is weakest. However, it is still possible for tropical systems to form within this boundary, as Tropical Storm Vimy and Cyclone Ugni did in 2001 and 2004, respectively. Movement. The movement of a tropical cyclone, that is its track, is typically approximated as the sum of two terms, steering by the background environmental wind and beta drift. The background environmental wind and beta drift